In this video lesson, we will begin exploring the quantum concept in the photoelectric effect. I have in front of me a calculator. We're going to be needing that as we hit some of our math type problems of our chapter, exploring how an electron travels indeed as a wave, even though it exhibits particle behavior, just as light exhibits duality in terms of energy and particle. Chemistry is the same way with its electron. We start to envision electrons traveling as waves around the nucleus. So we're going to do a little bit of review about the concept of wave mechanics. Understanding that the following terms might be brand new, they might be review for some of us. Electrons traveling around the waves traveling as waves around the nucleus of an atom, we're going to review some of what we call wave mechanics. If this represents a line as time is going by, we have to define some terms. And again, if they're brand new, you might even choose to draw this. This is a wave of energy traveling through space. If I draw a line directly through equal portions up and down, we have what's called the amplitude of the wave. Notice the amplitude is of equal distance up as it is down. The top of the wave is known as the crest. The bottom of the wave is known as the trough. A wave length is the measurement, the distance from crest to crest or trough to trough. We can also think of that as the distance. One complete up cycle and one complete down cycle. The distance here would be the wavelength. So we've got it measured three different ways. The wavelength from crest to crest, from trough to trough, or one complete cycle, one up, one down. That point of intersection all give us the same measurement, a wavelength. So the definitions written in words. The amplitude of a wave is the height of a wave from its origin. The wavelength is the distance between the crests. Its symbol is a Greek symbol. The symbol is known as lambda. And the Greek symbol, I tend to draw that just really as an upside down Y. The frequency is defined as the number of wave cycles to pass a given point per unit time. A frequency is given a Greek symbol. It's an N, N-U. Nu is how you pronounce that. It's more or less a squiggly V sign. The unit given to frequency is a per second. A per second is commonly called hertz, and that's after a person's name, so that's why it's a capital H. A hertz is the measurement called per second. Wavelengths typically measured in distance in the term meters. Frequency measured in per seconds, or a hertz. And a hertz is given that abbreviation HZ, capital H, small z. So placing this back on, the amplitude, the distance from the origin to the top of the crest. The wavelength, the distance from crest to crest or trough to trough. Wavelength is a distance, typically measured in meters. And a frequency is how long this wave takes to complete one cycle. From here to here is the completion of one cycle. The speed of light relates the inverse relationship between frequency and wavelength. The speed of light is given a constant c. c is equal to lambda nu. The speed of light is equal to the wavelength times the frequency. The speed of light is a constant. The constant has a value of 3.0 times 10 to the 8th meters per second. Light travels 3.0 times 10 to the 8th meters every second that goes by. If speed of light is in a meter per second, wavelength must be in a meter, and frequency is in a per second, meters per second, the unit for the speed of light. Another way of saying per second is the hertz. Hz, hertz, stands for a per second. Let's take a peek at some examples using this most likely familiar formula for us. The speed of light, 3.0 times 10 to the 8th meters per second. And we understand the formula that relates wavelength and frequency. The speed of light is equal to lambda nu. That squiggly little v represents frequency. The upside down y represents wavelength. Read with me our first example and have your calculator nearby as we get ready to solve our first problem. We're asked to calculate the wavelength of yellow light emitted by a sodium lamp if the frequency of the radiation is 5.1 times 10 to the 14th hertz. Our relationship, the speed of light constant, is equal to wavelength times frequency. The constant equals what we're looking for, wavelength, given the frequency of 5.1 times 10 to the negative 14th. 3.0 times 10 to the 8th meters per second, our speed of light constant. We're looking for wavelength when frequency is given as 5.1 times 10 to the 14th hertz, which I'll just remind us is a per second. Notice here, our measurement for wavelength will come out in a meter. Friends, this is basic algebra. We're going to take our 3.0 times 10 to the 8th and simply divide out the frequency to find the wavelength. Hit with me, please. 3.0 times 10 to the 8th, our speed of light constant. Factor out the frequency, 5.1 E14, and we get 5.88 times 10 to the negative 7th meters. Given the speed of light constant, divide out frequency, and we solve for the meters, the wavelength of yellow light. Now, keep in mind, I'm going to put back this chart that we had looked at earlier in our note pack. We're in the visible spectrum. Does that number make sense for where we're looking at? Notice here, these are wavelengths given to us in meters. Alrighty. Down here, they're nanometers. By the way, nano is 10 to the negative 9th. Alrighty. So thinking about the answer we just found, 5.88 times 10 to the negative 7th meters. Does that fall in the visible light spectrum? Well, it certainly does. We can see the negative 6th power to the negative 8th power. The answer we just found falls within the visible spectrum, which makes sense because we were told it was a yellow sodium lamp. The visible spectrum for sodium burns yellow. Number 2, what is the wavelength of radiation with a frequency of 1.5 times 10 to the negative 13th hertz? Again, C equal lambda nu. 3.0 times 10 to the 8th meters per second, the speed of light constant. We're going to find wavelength in a meter given the frequency of 1.5 times 10 to the 13th hertz. I'll write in, just for review, that hertz is a per second. We're going to start with our speed of light constant, 3 times 10 to the 8th power. We'll factor out the frequency, which was 1.5 E13. And we find a value of 2.0 times 10 to the negative 5th for our wavelength. Wavelengths are distances measured in meters. Does this radiation have a longer or shorter wavelength than red light? We're going to need to kind of access that spectrum again, and I just want us to kind of consider, maybe in a colored version, this will help. The electromagnetic spectrum, in which here, do you see the visible light range in between infrared and ultraviolet, the visible light range? The red giving us wavelengths down below here, 10 to the negative 6, and as the wavelengths get shorter, we start to move from Roy G. Biv, where the violet range is here. Alrighty, so taking light, such as that from sun, which is all colors combined, splitting it through a prism, we can see the visible light being spread out. That's based on the wavelength of the electrons traveling. This is now displayed here, where we can see shorter wavelengths compared to the longer wavelengths, reading in this direction. So we can see that that would end up to have a longer wavelength than red light. Alrighty, so did we see that? If red light is somewhere close to 10 to the negative 6th power, whoops, I'm not showing that very well. Here's the red light, a little bit between 6 and 7, but definitely a shorter wavelength with the negative 5 meters that we found here. Electrons travel as waves. The reason we're going through a little bit of physics review, if electrons travel as waves, they have a wavelength and they have a frequency. Wavelength and frequency are inversely related, yet when multiplied they always equal a constant known as the speed of light, 3 times 10 to the 8th meters per second. Every element has a unique number of electrons, therefore a unique arrangement, therefore a very specific light that is emitted from its electron configuration. Trying to make a tie-in of why we're studying wavelengths and frequencies, electrons travel as waves. What is the frequency? What frequency is radiation with a wavelength of 5 times 10 to the negative 6 centimeters? I know that my speed of light is 3 times 10 to the 8 meters per second. Sorry, I'm choking. 3 times 10 to the 8th meters per second. The wavelength is in a centimeter. So I'm going to just show, if this is a centimeter and this constant is in a meter, we must make like units. So we understand that in every 1 meter, there's 100 centimeters. Centi is the metric prefix for 100. Alrighty. So I'm going to use my conversion, just a metric unit conversion, to switch centimeters into meters. 5e negative 6 divided by 100 is 5 times 10 to the negative 8th meters. I cannot place a centimeter into the same problem that has a meter because the units don't cancel. So my wavelength in matching unit is 5 times 10 to the negative 8th meters. Now I can see the meters matching up to the speed of light constant. We're being asked to solve for the frequency. So our speed of light constant, 3 times 10 to the negative 8th, not 8, positive 8, sorry. 3 times 10 to the 8th power meters per second, divide out the wavelength of 5e negative 8, and we find a frequency of 6 times 10 to the 15th per seconds. I'll write that as hertz so we get used to being accountable for both. Now where does this fall in the electromagnetic spectrum? the wavelength given to us here in meters. Our wavelength was given as 5 times 10 to the negative 8th. What part of the spectrum are we in? Alrighty. It might be easier to see this in color. Frequency up at top, wavelength at the bottom of our chart here. This is just out of our chemistry book. Alrighty, so a couple of ways we could find the frequency we just solved for, or we can look at the wavelength given to us in the problem. The wavelength was 5 times 10 to the negative 8th meters. 5 times 10 to the negative 8th up here in the UV range. So where we're at in the electromagnetic spectrum would be in the ultraviolet range. Pause the video here and make sure that you can solve for either wavelength given frequency or solve for frequency given wavelength and where it falls on the electromagnetic spectrum. You have some sample homework problems that you should pause and look at as well right now. Start up your video again when ready. Let's now talk about the photoelectric effect. By studying black body radiation, German physicist Max Planck described mathematically that the amount of radiant energy, E, absorbed or emitted by a body is proportional to the frequency of the radiation. This equation, energy, is equal to Planck's constant times frequency, is often used to describe how much energy is being emitted or absorbed by an atom as its electrons are either jumping up to higher orbitals or falling back to lower orbitals. Let's use a Bohr model just for simplicity. If this represents the nucleus of the atom, in the first energy level we can place up to 2 electrons. In the next energy level we can place up to 8 electrons. We have a better view now of the quantum mechanical model, but allow me just for simplicity to draw an old-fashioned Bohr model, solar system. What I'm describing about black body radiation, energy is either absorbed by the atom, causing them to jump to higher orbitals. We call that an excited state. We can calculate how much energy is needed to absorb, for the atom to absorb for an electron to jump 1 energy level or 2 energy levels. Absorbing energy causes them to go up. They don't like to be at that higher energy level. When they fall back to their ground state configuration, they release energy. Falling back to the ground state releases energy, exothermic. Absorbing energy to go up to a higher energy level is endothermic, absorbing energy. So the purpose of studying this particular formula in chemistry, it's a crossover with physics, I'm aware, but it's in terms of jumping electron orbitals. Energy is equal to Planck's constant times the frequency of the radiation. Planck's constant is as follows: 6.63 times 10 to the negative 34 joules per second. Energy is measured in joules. Frequency is measured in a per second. Therefore, Planck's constant, if I think about what I've done, I have to multiply seconds on both sides to cancel those out, and we come up with this unit. 6.63 times 10 to the negative 34 joules second. Think of that as a multiply. The constant h is a constant, just like the speed of light. The constant is as follows. So E equal h nu, where that is the frequency. This constant is 6.63 times 10 to the negative 34 joules seconds. That's not a plural joule, but what that is joules times seconds. Let me get my screen back. Patience. There it is. Sorry about that. So in 1905, Albert Einstein comes along. We've heard his name, Nobel Prize winner. And he proposed that light could be described as a quanta of energy that behaves as if they were little particles he called photons. Photons, the little energy packets of light. Photons are what he actually won his Nobel Prize for. The photoelectric effect zaps metals, shiny metals like aluminum or tin. Those metals then eject electrons. When they absorb energy, they jump to higher electron. So therefore, when a light shines on them, they create photoelectric cells. It's, for instance, how automatic doors open at our Myers or other supermarkets. When you walk near the door, electrons, when you step on that entryway, you complete the circuit. A light shines on the cell, completing the circuit, called the photoelectric effect, and you can turn that into mechanical energy. So the doors would then open. Now that's not all important in terms of photoelectric effect and application, but what we're looking at is being able to excite electrons, causing them to jump to higher orbitals, and then ultimately falling back to the ground state and releasing that absorbed energy. That energy then can be trapped, made to do electrical work, turn it into a mechanical work, and we've got a door opening for us automatically. So these little tiny particles he called photons. Alrighty. So in the photoelectric effect, these metals can eject electrons when a light shines on them. Absorbing the light energy allows those electrons to jump orbitals. We capture that energy and put it to work. If E equals Planck's constant nu, E is energy measured in a joule. Planck's constant is a constant, 6.63 times 10 to the negative fourth joules times seconds. Let's take a look at some examples of how we can use the photoelectric effect in chemistry. We're going to be asked to calculate the energy in joules of a quantum of radiant energy. That's the energy of a single photon. It has the frequency of 5 times 10 to the 15th hertz. We're being asked to solve for energy. We'll take Planck's constant and simply multiply it by our frequency. The energy coming out in a joule is equal to Planck's constant, 6.63 times 10 to the negative 34 joules times second, times the frequency of 5.00 times 10 to the 15th hertz, or per seconds. Notice how seconds cancel. When I multiply those two numbers together, seconds cancel and we're left with a joule of energy. So with my calculator, let's hit Planck's constant, 6.63 E negative 34, times the frequency of 5 times 10 to the 15th power, and we find an answer of 3.32 times 10 to the negative 18th joules of energy. That's the energy of a single photon, a single electron, if you will, as it's traveling around the nucleus of an atom. What is the energy of a photon of a microwave radiation with a frequency of 3.2 times 10 to the negative, times 10 to the positive 11 hertz? Very similar to the problem we just solved. the energy of a photon of a microwave radiation of energy. So our energy is equal to 6.63 times 10 to the negative 34 joules times seconds, times that frequency of 3.2 times 10 to the 11th power per second, called hertz. Seconds cancel, and we've got a joule. On our calculator, 6.63 times 10 to the negative 34, Planck's constant, times 3.2 e positive 11, and I find 2.12 times 10 to the negative 22nd power joules of energy. If that's the energy for a single photon, the energy of a single photon, what is the energy of 1 mole of photons at this same frequency? Well, if the energy of a single photon can be represented by the following ratio, the number of joules of energy for every 1 photon. Suppose we have an Avogadro's number of photons. Photons then cancel. If that's joules for 1 proton, all we have to do is multiply that value by Avogadro, and we'll have how much energy for every mole of photons. So I'm going to multiply that by Avogadro, and I get 127.7 joules of energy. So for every single photon, quite small, but I start gathering whole moles of photons, it's such a large number, 127.7 joules for every 1 mole. I could probably put that as part of my unit. Joule per mole of photons. Let's read one more. The threshold photoelectric effect in tungsten is produced by the light of a wavelength of 260 nanometers. Give the energy of the photon. This looks like a double problem. We're going to have to change our wavelength into frequency and then sub in using Planck's constant to find energy. So given a wavelength, we have to manipulate that out to find frequency, to plug in to find energy. Another thing I noticed, 260 nanometers. That's like writing 260 times 10 to the negative 9th meters. Alrighty, so that's what this is referring to. And I have to be sure I place in meters into my speed of light constant, because the speed of light indeed is measured in meters per second. 3.0 times 10 to the 8th meters per second. I'm just going to write 260 times 10 to the negative 9th meters for my wavelength. Let's pull out the frequency. So nano is a metric unit given for the negative 9th power. 3 times 10 to the 8th, the speed of light constant. Factor out the wavelength, 260 times 10 to the negative 9th, and we get a frequency equal to 1.154 times 10 to the 15th per second, called a hertz. Hz would be another appropriate unit. But now I can simply take that value and multiply it by Planck's constant to find joules of energy. Planck's constant is 6.63 times 10 to the negative 4th joules times seconds. Multiply that by 1.154 times 10 to the 15th per second, and we've transferred that out to a joule. So while that's still on my calculator screen, I'm going to multiply that previous answer by Planck's constant. 6.63 times 10 to the negative 34. There, I got it correct. And I come out with, what did I do wrong? Clear screen. Planck's constant, 6.63 times 10 to the negative 34 times 1.54 to the 15th power Now I've got it. I must have hit a negative sign in an inappropriate place. Calculator error. 1.02 times 10 to the negative 18th joules of energy. Problem 3, we had a two-step problem. We were given a wavelength, but we can use our speed of light constant to change the wavelength into the frequency. Once we have the frequency, we use Planck's constant to find the joules of energy for that particular tungsten photon. Pause the video here. Pause the video and work some example homework problems on the photoelectric effect. You might even want to look at the sample or recommended problems from our homework. Make sure that you feel comfortable on the photoelectric effect before you move on to matter waves.